Hello, everyone. I'm Bruce Meyer, editor of Rubber and Plastics News. Welcome to the International Tire Exhibition and Conference organized by Rubber and Plastics News. We're certain you'll enjoy the variety of speakers and panel discussions offered throughout the conference. Our speaker today is Eric Pierce, a senior project engineer at Smithers Winter Test Center. Eric joined Smithers in 2016 and specializes in supporting engineering projects related to winter testing of tires and vehicles. He has specific expertise in winter traction testing for passenger, light truck, and truck tires. He previously worked as a lab manager for the Center for Tire Research at Virginia Tech. Eric is a committee member and sub-chairman for the ASTM International Technical Committee F9 on Tires, the Tire Performance Session Chair for Tire Society, and a member of the Industry Advisory Board for the Center for Tire Research. Eric will be speaking on tire performance testing for winter conditions and evaluating data. Let me now turn the discussion to Eric.
Thank you, Bruce. So basically, we're going to have an overview today of two ASTM standards, F1572 and F1650. F1572 is a standard test method for tire performance testing on snow and ice surfaces. What we're going to cover are what different tests are involved, some factors that may affect analysis, various types of test equipment and procedures, as well as a little bit into the data analysis and how reporting is done. Second standard we're covering is ASTM's F1650, which is a practice for how to evaluate tire traction performance data for different test conditions. Basically, we're going to look into the practices for assessing control tires in a sequence, how to determine if there's significant variation, and how to correct for control variations if there is significant variation. And finally, how to adjust test tires based on their sequence position. We're going to start out with 1572, which is these different test methods for winter surfaces. We're going to get into which different tests are actually involved in this. Road circuit handling, hill climb, winter slalom. We also have straight line acceleration and braking, as well as step steer. So the vehicle dynamics can and will influence this tire performance for these test types. These tests really are directed for specific vehicles and the tires on which they're tested. Results may vary with different vehicles as a result of different dynamics. So first, we're going to get into the factors that can affect this tire performance. There's a number of factors. This certainly isn't an exhaustive list, but we have temperature, ambient air surface, the tire temperature, solar heat load. The tire itself, factors include tire prep, how long is the break-in, zero break-in, tread depth, rim width, inflation pressure, as well as test load on the tire. The test surface itself, surface prep, the consistency, how level is the surface, CTI, which we'll get into a little later. If it's an ice surface, if it's burnished, as well as the mechanical breakdown of snow into ice crystals. A number of factors that can occur there. Test vehicle itself, vehicle condition, the brakes, the suspension, the dynamics, how is the suspension actually being affected, fuel and tire fitment as well. So the standard specifies with this chart, table E2, a number of environmental properties and the surface characteristics that occur there. I mentioned the CTI a couple of minutes ago. It's a Smithers device specified in the standard. Basically, there is a snow compaction level that can range from 50 up to essentially 100. And depending on the snow surface that you're looking for instance, medium packed snow has a CTI range of 70 to 80. And hard packed snow is from 80 to 84. Ice, dry ice, tends to be between 93 and 98. There are a number of different factors that we have to look into here, depending on which test surface you're looking to use. There's a certain range of minimum maximum for the snow or ice temperature, ambient air temperature maximums, as well as certain depth characteristics. This table definitely needs to be looked at and get into this type of testing. It's also used in that ASTM. What type of test equipment are used? Generally, there's some combination of a time, speed, and distance measurement. This could include a fifth wheel, a non-contact optical sensor, accelerometers with GPS, or wheel speed. The lower right's a picture of a typical V-box setup that we use for acceleration and braking testing. So, getting back into the specific tests, here's some more details with road circuit handling. The picture is one of our specific small handling courses, Area 8 at the Smithers West track, test track. So as a whole, the goal for this is actual road performance. You have varying conditions that are set up on the test track. It's typically packed snow. You could have loose snow. You can have patches of ice if desired. The track is usually at least 1 kilometer long. You've got to have some hills, some curves, hill acceleration locations, downhill braking, as well as some high-speed sections. You don't want more than a 6 to 10% grade maximum on some of the hills. So the procedure itself starts out with basically you're just using a timing device to track lap time. You can also optionally record acceleration data longitudinally. We start this test from a dead stop. You're accelerating to the maximum limits for the specific conditions. And at the end, you have a maximum deceleration to end the course. For each particular lap, you want to record subjective notes on the handling of the vehicle. You get at least 2 runs in per set of tires. Very important to note is that every test sequence needs to begin and end with a control tire. Typically, these tests allow for 2 to 3 test tires in between control tires. So, for instance, we have control 1, test 2, an optional test 3, and then back to a control 2. So just a little bit on the data analysis and reporting. The goal is to summarize test results for the individual tires. The handling results should, at the bare minimum, contain the lap times, the multi-point subjective evaluation, means for control loss. So how is the control loss actually getting calculated readings, comparing the elapsed time of the test to the controls. If you do use the optional acceleration data, you can also use that to relate traction loss and controllability in the hill and curve sections. And then ideally, you also want to get the maximum longitudinal lateral acceleration capabilities based on each particular tire. So moving on to the next test this covers, winter hill climb. Goal for this is just driving traction evaluation. So you need to have a consistent surface. It's either going to be packed snow or dry ice. You can either have a parabolic or constant grade. It starts out with 0% up to a maximum of 15% for snow, and 0 to 10% grade for ice. Then there's specific track requirements from a minimum of basically 61 meters long and 6.1 meters wide. Test procedure is pretty simple. You're recording time to travel the course distance. This one also starts from a dead stop. You accelerate to your maximum attainable speed, and what your measuring criteria are for your best time, as well as the maximum grade able to be attained. So then you're going to want to repeat this test for each individual tire at least 4 times. Same as with the others, you have to start the sequence with a control tire and then a control tire. And to prevent inertia effects, you really may need to limit throttle to keep from spewing the data. As far as data analysis goes, same with the others, you want to have individual results per tire. You want to know what the max grade attained is if the full grade is not able to be accomplished. Time to complete the hill climb or time until stalling. Control loss method, basically how is the tire failing. Subjective comments, and then calculate readings comparing the average climbing performance to the individual tire. And finally, calculated elapsed time ratings for each particular tire. Now, this particular hill climb can be used to correct the data using ASTM F1650, which we're going to get into a little bit later. So winter slalom has a focus on lateral tire performance. On the left side, we've got a images taken from ASTM 1572, showing some typical slalom courses. You want to have a consistent packed snow surface or dry ice surface. Snow tends to be a little more common. You have at least 6 cones to prevent transit vehicle dynamics from influencing the test results. I want minimum cone spacing between 15 to 30 meters. Cone spacing can be uniform or decreasing, so you have a tighter reading set there for each particular group. And a minimum width of at least 3.6 meters. Test procedure here is the same instrumentation as road circuit handling. I want to record the best effort time to travel a course and the maximum lateral acceleration. This also is started from a dead stop at a cone. You're going to accelerate to a maximum speed, perform the course with a constant speed. The goal is to maintain the same speed throughout so you can compare lateral acceleration. And each run, you're going to increment the speed until you get to the point where it goes from controllable to being a control loss. So then you're going to want to get at least 4 runs with each particular tire set once you're at that control or right below the end stage of control loss. The same as with the others, start and stop the test sequence with the control tire as well. Results are pretty simple. Want elapsed time, maximum lateral acceleration, description for the control loss, some calculated readings for the elapsed time, and then calculated readings comparing the peak lateral traction of each individual tire to the controls, and then subjective comments as well. Given your control tire data, this one can also be corrected F1650. So acceleration and braking are both used to provide discrete straight line characteristics of longitudinal traction. Versus packed snow or ice, smooth level surface, you're going to need at least 500 feet, 12 feet of width. Almost always with this, we tend to use Race Logic, GPS, and accelerometer-based equipment. This standard specifies that you're testing from 1 to 30 miles per hour. The goal is to accelerate as quickly as possible with minimum tire slip over the time. Sandwich 2 to 3 test tires between control tires. So braking is from 30 or 40 miles per hour to 0. It's to travel down the lane at the appropriate speed, make sure there's no transient effects of the vehicle steady state velocity before test occurs, and apply full brake force, or you can modulate the brakes to minimize lockup. But whichever you do, you have to make sure you follow the same pattern for all repetitive tests. And then you're going to record the measured initial speed with a plus or minus 3.2 kilometers per hour, the chosen speed. So basically, you have to have some consistency. You're given initial velocity, braking. Then you're going to record the stopping distance. This can also use ASTM's F1650 for data analysis. You're going to want to get at least an average of the 5 best times per tire for the acceleration. For the braking, we're going to calculate the average time, and there's basically a correction factor for determining what the corrected brake distance is given the change in actual initial velocity. So then we're going to compare the relative performance of each tire to that of the controls. Final test is step steer that 1572 covers. This is to provide a discrete maximum lateral traction. It also has subjective analysis of the vehicle response. Use similar course to the slalom. It's basically the way this test works is that you are going to continuously record lateral acceleration. You perform a sequence of maneuvers at appropriate speed to find this max lateral acceleration. You drive down a lane at a specific speed, then you're going to turn the steering wheel at 180 degrees as quickly as possible. Once the vehicle stabilizes, then you're going to correct the steering again and recover straight ahead. You perform this in both left and right lane changes, and then perform multiple runs per tire set. And what we're looking for here also is a subjective evaluation of oversteer, understeer, what the steering response is, and the vehicle recovery. Same as all the others, we summarize individual results per tire. You may have to correct the data using F1650. And what we're ideally looking for is the peak and average lateral acceleration for each run, and comparing the relative performance to that of the controls and the subjective evaluation. So now we're going to get into standard ASTM's F1650. This is the actual practice for evaluating tire traction data for different test conditions. This isn't strictly for low-new surfaces like snow and ice. It can also be used to correct for high-new surfaces. So first on the list here is what practices can we use to assess the control tires? How are we going to find out if there is significant variation? How are we going to correct for the control variations? And then how to adjust the test tires based on the sequence if there is significant variation. So this standard breaks it down to two different methods. And it really just comes down to what is your reference. Method A uses the first control tire, the average of all the control runs, as your reference. Method B uses an average of all of the control runs. They both use the same methodology, same calculations. It all just comes down to a different reference point. They do have different absolute traction values, but the same relative traction rating. So ultimately, they give us the same results, relating one tire to another. So this method A, well, actually all these methods use two different test sequences. I mentioned this briefly earlier, but basically you can have control one with two test tires in between the second control, or you can have three test tires between control runs, which is where C1, T1, T2, C2, that's two test tires, and the one below it is for a three test tire sequence. This is important to remember for later. Let's get into the actual method A summary. The benefits of this one too is that it corrects everything to this initial level of C1. It also allows corrections to be made after just a couple of runs. Method B requires the entire test sequence to be completed before you can do corrections. So here, for method A, we've got three different potential methods of, not methods, types of control data. On the left is 8 different runs. These are acceleration times in seconds, is what I have on the vertical axis. Horizontal axis shows the average of each control number. So we have 8 tests, 8 acceleration tests. The orange line gives us our first control value. It's just our baseline for which everything is compared to. Whereas the blue plots, the blue dots are showing us what the actual test data was for each of the individual 8 control runs. This specific plot doesn't have any corrections that are needed. This is just average variation trend that can occur. If you look on the top right, we've got some linear drift that's occurring. This would require correction using these methods. You'll notice each particular control tire sequence is increasing over time. This could be a number of factors, typically environmental changes, changes in snow or temperature. This is why we have these. On the lower right, we're getting a transient shift, where basically an abrupt increase in the control, the time for the acceleration in seconds before it returns back. This also would require corrections to the data in order to compensate for the transient shift that occurs. So with this method A, this specifically we're going to be covering for the linear sequence coming back here. So the graph on the top right, this particular method here is used to correct for changes in controls over time. So first thing to do is we pull up this table in the ASTM 1650. It's table 2. Basically just shows us the correlation coefficient critical values depending on the number of degrees of freedom. Degrees of freedom is determined by the number of pairs of control sets minus 2. So in our graphical examples on the previous page, we had 8 control samples, so we would have 6 degrees of freedom. So we would find the critical value for the correlation coefficient based on this, in this circumstance, 0.706, and we would calculate our correlation coefficient of our control runs. as compared to the initial control reference. So if I'm coming back here for a moment, if you look at the top right, that first data point for control 1 is our reference. So basically, we're going to see how all these control runs are for their correlation coefficient as compared to that first reference point. If this calculated correlation coefficient is greater than the tabulated one from the table, then there is considered to be significant drift. If that's the case, then we do need to apply corrections to the tire test data. So that covers for linear. Now, in circumstances where we have transient variations, there's two different types that we have to account for. Type 1 is if we have a drop shift, if you look at the graph on the left, turns back to our regular pattern. Whereas type 2 is a shift, stepwise shift that occurs in our control tire data, and it does not return. These two different types of transient variations and different methods for evaluating and compensating for it. So type 1, our transient shift that returns, first thing we're going to do is calculate the standard error for the mean regressing line. Mean regression line. Up back in the table, that would be our orange line, which is essentially in line with the first 3 points, the last 3 points. Then we're going to calculate the standard error for offset points, which is going to be considered SE. So the two methods define significance based on the number of points. There's one based on 3 or less control points, or one based on 4 or more. For that, I'm going to refer you to section 8.4 of ASTM F1650, which is too much to cover in a smaller time period. Then going to stepwise transient shift, which is our type 2. Basically, you just calculate the standard error for the first trend line, one for the second trend line. If we take a look at the graph on the lower right, the first 4 points are our first trend line, and those last 4 points, we would have standard error for those 4 points as well. And then basically, we're going to determine if that drift is significant between the two, if the difference between the standard error of the first and the second at the offset are greater than 2 times standard error, first regression line and second regression line. So in the event that we do have significant drift, whether it's for the linear or the stepwise or transient, methods, 2 different methods for applying correction factors. Plan A is for 2 test tire sequences. So basically, we've got a correction factor F of I for each consecutive pair of control tires. So control 1 and 2, if you look at the bottom, are going to be associated with correction factor 1, C2, and C3 for F2, and so on. So basically, you're just going to take the first control, second control, and divide it by 2 times the second control. So then we're going to apply Fi to the candidate values. In order to do this, we're going to, as an example, take F1, use that to apply to candidate tires between C1 and C2. In this circumstance, we had 2 test tires, T1 and T2. So to correct T1, it's T1's original value divided by the correction factor F1. T2 is corrected by T2's original divided by second batch of control tires. So we have T3 and T4, which are respectively created by T3 divided by F2's correction factor. Pretty simple procedure. Just follows along. So plan B is for a 3 test tire sequence. Basically, you've got a correction factor, same as the other, that's applied to each individual test tire. The difference on this is we have T1, T2, T3. T2 is our middle tire. It gets half of its weighting from the first control, half from the second control, whereas T1 gets 3/4 of its weighting from the first control and only 1/4 from the second. So the converse for the third test tire. This pattern just repeats itself for each block of control tires. A little quick to go through it, but the standard has some good tables that make this pretty easy to follow. So our method B summary is our second method for accounting for drift. Remember, method A was using our first control tire as our reference point for comparison for all of the controls, whereas method B uses the grand average of all of our control test units as a reference. So if you take a look at the plot in the top right, you'll see that orange line that is right at the average of all of these control tires. That's the method we covered. First method, method A, uses that first control as a reference, which is also that orange line in the bottom right. But just notice that you have a different reference point for which everything's compared to. The grand average has a higher precision compared to method A because you have more values. Also a benefit with this method is that there isn't a statistical test of significance for your trends or shifts, but you can only make corrections after the whole test is complete. Or just to note that method A and method B both have the same relative traction ratings. Absolute values of the ratings are not identical, but relative comparisons are the same. Method B, it's not too bad. Basically, we just get our control average of all the values. So if we take our first control sequence, control 1 and control 2, with the 3 test tires in between, we're just adding the first and second control and dividing it by 2 times the control average. So basically the same procedure as the last, you're just using the control average instead of your C1 as your reference point. Same as the candidate values, basically the same exact correction method. Your T1, so test tire 1 corrected is just your T1 original value divided by your correction factor for F1. That same procedure follows as long as the method. So basically, what we've covered is 2 different test standards in way too short of a time period. But first was standard test methods for how to perform tire performance testing on snow and ice winter surfaces. We had 6 different test types that give you some basic factors that you could consider that could affect the quality of your results. Very brief overview on what type of test equipment and procedures would be used, and a very, very short summary on what the data analysis of the reporting is. Then we also covered ASTM 1650, which was a way to actually evaluate the control test tire data from these tests. And we had 2 different methods based on your control reference, whether it was the initial or the average control that was used. 3 types of correction based on the changes in the trends. And then 2 different test sequence types for 2 or 3 test tires that basically dictate how you go ahead and adjust your test tire data if there is significant drift. So if you have any questions, thank you very much for your time, and I'm going to turn it back over to Bruce.
Thanks so much for your presentation, Eric. I would also like to thank our audience for attending this session of iTech, and thank you to our sponsors for supporting iTech Virtual 2020. If you want to revisit this session or any others from the conference, they will be available on Rubber and Plastics News website, rubbernews.com, after the event is completed. If you would like to purchase papers from this and other sessions of iTech, visit itech-tireshow.com to do so. Don't forget that you can connect with your colleagues here through the virtual networking program, which can be found on the left side of your screen. Simply click the Meet icon to start connecting with fellow iTech attendees. Thanks for joining us today.